Earth moves in patterns. Day becomes night. Seasons shift. Oceans rise and fall with quiet precision. Most of these cycles are predictable, stable, almost comforting. But not all of them, because hidden within the vast Pacific Ocean, there is a cycle that doesn't follow simple rules. A system driven by wind, water, and heat, constantly moving, constantly adjusting, yet never entirely predictable. Every few years, something changes. The winds begin to weaken, warm water spreads across the ocean, and the balance that normally holds everything together starts to break. This phenomenon is known as El Niño, a name that sounds almost gentle, almost harmless, but its effects can reach across the entire planet. Floods in some regions, droughts in others, shifts in weather that affect ecosystems, food systems, and human life. And often, these changes begin quietly, far beneath the surface, long before we notice them. But El Niño is only one side of a larger system, because the ocean does not simply lose balance. It swings between two powerful phases, constantly redistributing heat across the Earth, shaping weather in ways we don't always expect. And if you enjoy calm, cinematic explorations like this, you can subscribe to Theories Before Sleep, because tonight we're going to slow down and explore how a single shift in wind and water can ripple across the entire planet and quietly reshape the world around us. To understand El Niño, we have to begin with something that usually goes unnoticed. The Pacific Ocean. Not just any ocean, but the largest body of water on Earth, stretching across nearly a third of the planet's surface, from the western coasts of the Americas to the shores of Asia and Australia. At first glance, it appears calm, vast, unchanging. But beneath that surface, there is constant motion. Winds moving across the equator, water shifting in response, heat being transferred from one side of the ocean to the other. This movement is not random. It follows a pattern, a stable system that maintains balance. Under normal conditions, strong winds blow steadily from east to west across the equator. These are known as the trade winds. They are driven by Earth's rotation and by the uneven heating of the planet. Warm air rises near the equator. Cooler air moves in to replace it. And as the planet spins, this flow bends, creating a steady push of air across the Pacific. These winds are not dramatic. They don't arrive as storms. They don't draw attention. But they are powerful because they act continuously, day after day, year after year. And as they move across the ocean, they drag the surface water with them. Warm water from the eastern Pacific, near South America, is pushed westward, toward Indonesia and Australia. Over time, this creates a difference. The western Pacific becomes warmer. The eastern Pacific becomes cooler, not by a small margin, but significantly. Because as warm water is pushed away from the Americas, something rises to replace it. Cold water from the depths of the ocean. This process is called upwelling, and it is essential because that cold water carries nutrients, minerals, that have settled in the deep ocean over long periods. When they rise to the surface, they feed microscopic life, phytoplankton, tiny organisms that form the base of the marine food chain. Fish feed on them. Larger fish feed on those fish. And entire ecosystems depend on this cycle. From the smallest organisms to the largest predators, all supported by this quiet movement of water. So under normal conditions, the Pacific Ocean is not just stable. It is productive, alive, balanced. But this balance depends on one thing: the strength of the trade winds. As long as the winds remain steady, the system continues. Warm water moves west. Cold water rises in the east. Ecosystems thrive. Weather patterns remain predictable. But if something changes, if those winds weaken, even slightly, the entire system begins to shift. And this is where El Niño begins. Not as a sudden event, but as a disruption, a gradual breakdown of normal conditions. The trade winds lose strength. They slow down. And as they do, they stop pushing warm water as effectively. Instead of being carried west, that warm water begins to spread back toward the central and eastern Pacific, toward the Americas. At the same time, upwelling weakens. Cold water no longer rises as strongly. Nutrients remain trapped in the deep. The surface becomes warmer, but less productive. And this shift changes everything. Because the ocean and the atmosphere are connected. What happens in the water affects the air above it. Warm water heats the air, causing it to rise. And as air rises, it creates low pressure. This draws in surrounding air, altering wind patterns, changing the movement of clouds, and ultimately reshaping weather across vast distances. This is not a local effect. It does not stay confined to the Pacific. It spreads, influencing weather systems around the world. But at its core, El Niño is simple. It is the weakening of a system that normally maintains balance. A shift in wind, a change in water movement, a redistribution of heat. And from that shift, a chain reaction begins. In South America, warmer waters reduce marine life. Fish populations decline. Fisheries struggle. At the same time, warmer air leads to increased rainfall. Regions that are usually dry experience flooding. Rivers overflow. Land becomes unstable. Communities are affected. But the impact does not stop there. Across the Pacific, conditions reverse. In Australia and parts of Southeast Asia, the reduction of warm water means less rainfall. Drought conditions begin to develop. Crops fail. Water becomes scarce. And in some cases, wildfires become more likely. In North America, jet streams shift. These are high-altitude winds that guide weather systems. When they move, they change the path of storms. Some regions become wetter, others become drier. Temperatures shift. Winter patterns change. And all of this originates from a subtle change in the Pacific Ocean, a weakening of wind. a shift in water, something that begins quietly but spreads across the entire planet. This is what makes El Niño so important. It is not just a regional phenomenon. It is global, a system that connects oceans and atmosphere across continents. And yet, it is not constant. It does not happen every year. It appears in cycles, irregular, unpredictable in exact timing, but recurring. Every few years, the conditions align. The winds weaken, the ocean shifts, and El Niño returns. Sometimes mild, sometimes severe, but always capable of altering the balance. And this raises an important question. If El Niño is a disruption, what does the system look like when it moves in the opposite direction? Because the Pacific Ocean does not simply return to normal. It often swings beyond it, into a different state, a phase that strengthens the very forces El Niño weakens. And that phase is just as powerful. But for now, what matters is understanding this first shift, the moment when balance begins to break, when the ocean changes and the atmosphere follows. Because everything that happens next depends on this interaction between wind, water, and heat. A connection that is always present, but only becomes visible when it begins to change. When El Niño begins, it does not announce itself. There is no sudden storm, no dramatic shift that can be seen in a single moment. Instead, it starts quietly, with a change so subtle it can go unnoticed. The trade winds weaken, not completely, not all at once, but enough to slow the steady push of warm water across the Pacific. And when that push weakens, the system that depends on it begins to change. Under normal conditions, warm water is carried west. It gathers near Indonesia and Australia, stacking up over time, creating a deep layer of heat. But now, that movement slows, and the warm water begins to spread, not just westward, but outward, back toward the center of the ocean, and further east toward the Americas. At the same time, something else begins to fade. Upwelling, the process that brings cold, nutrient-rich water to the surface. As the winds weaken, there is less force pulling surface water away from the coast, which means less space for deep water to rise. And without that rising water, the ocean surface changes. It becomes warmer, but less alive, because the nutrients that sustain marine ecosystems remain below, out of reach. This is one of the first visible signs. Fish begin to disappear, not instantly, but gradually. They migrate, searching for colder waters, for regions where food is still available. And as they move, entire food chains are affected. Birds that depend on fish struggle. Larger predators follow their prey, and the balance that once supported life along the coast begins to collapse. But this is only the beginning, because the ocean does not exist alone. It is part of a larger system, connected to the atmosphere above it. As the surface warms, it transfers heat to the air. The air becomes lighter. It rises, and rising air creates low pressure. This draws in surrounding air, altering wind patterns, changing the direction and strength of atmospheric movement. Clouds begin to form in different regions. Rainfall shifts. Weather patterns adjust. And this is where the effects begin to spread. Because once the atmosphere changes, those changes are carried across the planet. In the eastern Pacific, near South America, warmer water leads to increased evaporation, more moisture in the air, more clouds, and eventually more rain. Regions that are normally dry become wet, sometimes extremely wet. Rivers swell. Soil becomes unstable. Flooding begins. And in severe cases, the impact can be overwhelming. But while one region receives too much water, another begins to lose it. Across the Western Pacific, in places like Indonesia and Australia, the opposite occurs. With less warm water, there is less heat transferred to the atmosphere. Air does not rise as strongly. Cloud formation decreases. Rainfall declines. And drought conditions begin to develop. This contrast between East and West is one of the defining features of El Niño. Too much rain in one place, too little in another. A redistribution of water across the planet. But the effects do not stop at the Pacific. They extend further because the atmosphere is interconnected. Air currents carry these changes across continents. One of the most important of these currents is the jet stream, a fast-moving band of air high in the atmosphere. It guides storms, shapes weather patterns, and during El Niño, it shifts. In North America, the jet stream tends to move south. This brings wetter conditions to the southern United States, while the northern regions become warmer and drier. Winter patterns change. Snowfall decreases in some areas. Rain increases in others. And these shifts can influence everything from agriculture to water supply. In other parts of the world, similar changes occur. In South Asia, monsoon patterns can weaken. Rain arrives later or in smaller amounts. This affects crops, food production, and in extreme cases, can lead to shortages. In Australia, dry conditions increase the risk of wildfires. Vegetation dries out. Land becomes more vulnerable, and a single spark can spread rapidly. Across Africa, rainfall patterns shift as well. Some regions become wetter, others drier, and each change affects the people and ecosystems that depend on stable conditions. All of this from a shift in wind and water in one part of the ocean. This is what makes El Niño so powerful. It is not localized. It is global. A system that connects distant regions through shared processes. But it is also variable. Not every El Niño is the same. Some are mild, producing only small changes. Others are intense, creating extreme conditions, floods, droughts, heat waves, and the difference between them is not always predictable because the climate system is complex. It responds to multiple influences: ocean temperatures, atmospheric conditions, long-term climate trends, all interacting, all shaping the outcome, which is why no two events are identical, even though they follow the same general pattern. And despite decades of study, there are still uncertainties, questions about how strong an event will be, how long it will last, and exactly how it will affect different regions. But one thing is certain: El Niño is not an isolated event. It is part of a larger cycle, a system that moves between phases, between disruption and restoration. Because eventually, the conditions that create El Niño begin to change again. The winds strengthen, the ocean shifts back, and the system moves toward balance. Or sometimes, beyond it, into a different state altogether, one that intensifies the normal conditions rather than weakening them. But before we explore that phase, it's important to understand this one fully. Because El Niño is not just about change. It is about imbalance. A temporary state where the forces that normally keep the system stable are reduced. And when that happens, the entire planet responds. Through wind, through water, through weather, and through the lives of everything that depends on them. A reminder that even the smallest shift in the right place can have consequences on a global scale. El Niño is not the whole story. It is only one phase of a larger system, because the Pacific Ocean does not simply return to normal after a disruption. It often shifts further, in the opposite direction, into a state that strengthens everything El Niño weakens. This phase is called La Niña. If El Niño is a loss of balance, La Niña is an intensification of it. A system pushed beyond its usual state, where the forces that shape the Pacific Ocean become stronger, more defined, more extreme. To understand La Niña, we return to the same place, the equatorial Pacific Ocean, where winds, water, and heat are always in motion. But now, the pattern is different. The trade winds do not weaken. They strengthen, blowing faster, more consistently, pushing surface water westward with greater force. Warm water piles up even more in the western Pacific, near Indonesia and Australia. The difference between east and west becomes larger, more pronounced. And as that warm water moves away from the Americas, something else increases. Upwelling. Cold water rises more strongly along the coast of South America, bringing nutrients to the surface, fueling marine life. Phytoplankton flourish. Fish populations grow. Ecosystems become highly productive. In this phase, the ocean is not just balanced, it is energized. But this energy does not stay confined to the water. It moves into the atmosphere. Because colder surface waters in the eastern Pacific mean cooler air above, air that is less likely to rise, less likely to form clouds, less likely to produce rain. So along the western coasts of the Americas, conditions become drier. In some regions, drought begins to take hold. Rainfall decreases. Water becomes scarce, and the land responds. But across the Pacific, the opposite happens. In the western regions, where warm water accumulates, air rises more strongly. Clouds build. Rainfall increases. Storms become more frequent. In Southeast Asia, monsoon systems intensify. Flooding becomes more likely, and tropical storms can grow stronger. In Australia, the increased moisture leads to heavy rainfall. River systems swell. Land becomes saturated. And in some years, flooding reaches catastrophic levels. So once again, we see the same pattern. A redistribution. Water shifting from one region to another. But in reverse, where El Niño brings rain to the east, La Niña brings it to the west. Where El Niño creates drought in one region, La Niña creates it in another. A mirror image, but not a perfect one, because the system is not symmetrical. Each phase has its own characteristics, its own variations, its own impacts. And just like El Niño, La Niña affects regions far beyond the Pacific, because the atmosphere connects everything. Changes in one area ripple outward, influencing weather patterns across continents. In North America, the jet stream shifts again, but this time it moves north. Storms are directed toward the Pacific Northwest, bringing increased rainfall to that region. While the southwestern United States often becomes drier, drought conditions can intensify, water reserves decline, and long-term impacts begin to accumulate. In the Atlantic, La Niña has another effect. It can increase hurricane activity because atmospheric conditions become more favorable. Winds are less disruptive to storm formation, allowing hurricanes to develop more easily and sometimes more intensely. So while one part of the world experiences heavy rain, another faces storms of a different kind. This is the nature of the system. Interconnected, complex, capable of producing multiple outcomes at once. But despite these differences, La Niña shares something with El Niño. It is temporary. It does not last forever. Like its counterpart, it exists within a cycle, a shifting balance between opposing forces, winds strengthening, then weakening, water moving, then redistributing, heat transferring, then stabilizing. Over time, the system moves back toward neutral conditions, a state where the Pacific Ocean returns to its baseline, where trade winds are steady, where warm and cold waters are distributed as expected, where weather patterns become more predictable. But even this neutral state is not permanent, because the cycle continues, shifting again, returning to El Niño, or moving back into La Niña, over and over, every few years, not on a strict schedule, but with a rhythm, a pattern that emerges over time. And this pattern has been present long before it was understood. For centuries, people observed its effects. Fishermen noticed changes in ocean temperature, changes in fish populations, changes in weather, but they did not know the cause. It was only with modern science that the connection became clear. That these events were not isolated, but part of a global system, the El Niño Southern Oscillation, or ENSO, a cycle that links ocean and atmosphere, connecting distant regions, influencing climate on a planetary scale. And even now, after decades of research, there is still more to learn. Because while the general pattern is understood, the details are not always predictable. Why some events are stronger than others, why timing varies, how global warming might influence the cycle. These are still open questions, and they matter, because as the climate changes, the behavior of these cycles may change as well, making their impacts more intense, more frequent, or more unpredictable. But even without those uncertainties, one thing is clear. El Niño and La Niña are not separate phenomena. They are connected, two sides of the same system, a continuous movement between imbalance and excess, between weakening and strengthening. And through this movement, the planet adjusts, redistributing heat, water, energy, maintaining a dynamic equilibrium, a balance that is never static, but always shifting. And as it shifts, it shapes the environment, influences ecosystems, affects human societies, and reminds us that even the largest systems on Earth are governed by interactions that begin in a single place, with a change in wind, a movement of water, and a cycle that never truly stops. By now, the pattern is clear. A change begins in the Pacific Ocean. The winds shift, the water moves, and from that movement, a chain reaction spreads. But how does something that starts in one ocean reach the entire planet? How does a shift in wind and water influence weather thousands of kilometers away? The answer lies in connection. Not a visible connection, but an invisible one. A network of air currents, pressure systems, and temperature differences that link distant regions together. The atmosphere is not divided. It is continuous, a single system moving around the Earth. And within that system, small changes can travel, expanding outward, influencing areas far from their origin. This is how El Niño and La Niña extend their reach, through the movement of air, because when ocean temperatures change, they alter the behavior of the atmosphere above them. Warm water heats the air. Cool water allows it to remain stable. And these differences create pressure changes, areas of low pressure and areas of high pressure. Air moves between them, always seeking balance. And as it moves, it carries energy, heat, moisture, momentum. Across vast distances, this movement forms patterns, large-scale circulation systems that shape global weather. One of the most important of these patterns is known as the Walker circulation. Under normal conditions, warm air rises in the Western Pacific. Near Indonesia, where warm water is concentrated, This rising air creates clouds, rain, storm systems. Then the air moves eastward at high altitude, eventually cooling, descending over the eastern Pacific, near the Americas, creating drier conditions. From there, the air flows back westward near the surface, driven by the trade winds, completing the cycle. This circulation is stable, predictable. It helps maintain the balance of heat across the Pacific. But during El Niño, this system weakens. Because warm water spreads eastward, the region of rising air shifts. Clouds and rainfall move with it. The Walker circulation loses its strength, becomes less defined, less stable. And this change affects everything connected to it. Storm systems shift, rainfall patterns change, pressure systems adjust, and these adjustments spread outward, across the atmosphere. In La Niña, the opposite occurs. The Walker circulation strengthens. The contrast between east and west becomes sharper. Air rises more intensely in the western Pacific and descends more strongly in the east. The system becomes more pronounced, more active, and once again, this influences weather across the globe. But the Walker circulation is only one part of the story. There are other systems, other pathways through which these changes travel. One of the most significant is the jet stream. High above the Earth, narrow bands of fast-moving air circle the planet. These jet streams guide weather systems. They determine where storms go, where temperatures rise or fall. And during ENSO events, their position changes. In El Niño years, the jet stream often shifts south, redirecting storms toward different regions, bringing rain to some areas and leaving others dry. In La Niña years, it shifts north, creating a different pattern, a different distribution of weather. And because the jet stream affects large regions, these shifts can influence entire continents. But even this is not the full picture, because the climate system is layered. Ocean currents, atmospheric circulation, land surfaces, all interacting, all influencing each other. And when one part changes, the others respond. This is why the effects of El Niño and La Niña are not identical every time. The system is dynamic. It reacts to multiple inputs, temperature differences, seasonal variations, long-term climate trends, all shaping the final outcome. So while the general pattern remains, the details vary. Some regions may experience stronger effects, others weaker. Some impacts may arrive earlier, others later, but the connection remains. A link between ocean and atmosphere that allows a single change to influence the entire planet. And this connection is not new. It has always existed for thousands of years, long before it is understood, long before it was named. People observed its effects, changes in rainfall, unusual weather, shifts in seasons. But they could not see the cause. They could not trace it back to a change in the Pacific Ocean, Today, we can, through satellites, through measurements, through models that track the movement of air and water, we can observe the system as it evolves. Watch the ocean temperatures change. Monitor the strength of the winds. Track the movement of pressure systems. And from this information, we can make predictions. Not perfect ones, but useful. Predictions that allow preparation, planning, adaptation. Because understanding the system gives us time. Time to respond to changing conditions, to prepare for floods, for drought, for shifts in weather that might otherwise arrive without warning. And this is one of the most important aspects of studying ENSO. Not just understanding how it works, but using that understanding to reduce its impact, to adapt to a system that will continue whether we are ready or not. Because ENSO is not something that can be stopped. It is part of the Earth's natural behavior, a cycle that redistributes heat, balances energy, maintains the dynamic nature of the climate. And as long as the Earth continues to rotate, as long as the ocean and atmosphere interact, this cycle will remain. Shifting, changing, connecting distant parts of the planet through invisible pathways. A reminder that nothing in the climate system exists in isolation, that everything is linked, and that even the most distant regions can be connected through the movement of air and water. Across the entire Earth, not every El Niño is the same. Some pass quietly, barely noticeable. A slight shift in temperature, a small change in rainfall, something that only instruments detect. But others are different, stronger, more disruptive. Events where the balance does not just shift, but breaks. Where the ocean warms far beyond its usual range. Where the atmosphere responds with greater intensity. And where the effects are felt on a global scale. These are the extreme events, moments when the cycle reaches its limits. And when it does, the consequences can be severe. To understand why, we have to look deeper. Because an extreme El Niño is not just a stronger version of the normal pattern. It involves amplification, feedback, processes that reinforce each other, making the system more intense. It often begins the same way. The trade winds weaken. Warm water spreads eastward. Upwelling decreases. But then, something changes. The warm water does not stop moving. It continues, spreading further, covering larger areas of the Pacific, increasing the surface temperature over vast regions. And as the ocean warms, the atmosphere responds more strongly. Air rises more rapidly. Cloud systems expand. Rainfall intensifies. This creates a feedback loop because rising air reduces surface pressure and lower pressure weakens the winds even more, which allows more warm water to spread, which increases the temperature further. And so the cycle reinforces itself, growing stronger over time. This is what drives extreme El Niño events, a system that feeds into itself, pushing beyond normal limits, And when it does, the impacts become more pronounced. In South America, rainfall can become overwhelming, not just increased, but excessive. Floods that exceed the capacity of rivers, landslides triggered by saturated soil, infrastructure overwhelmed, communities displaced. These are not gradual changes. They happen quickly, sometimes without enough time to respond. At the same time, other regions experience the opposite. In Southeast Asia and Australia, drought conditions intensify. Rainfall decreases dramatically. Water supplies shrink. Agriculture suffers, and the land becomes more vulnerable to fire. Vegetation dries out. Forests become unstable, and once ignited, fires can spread rapidly across large areas, causing damage that can take years to recover. In Africa, some regions experience severe drought. Others receive intense rainfall, patterns that disrupt agriculture, food systems, and local ecosystems. In North America, extreme El Niño events can alter winter patterns significantly. Storm systems shift. Some regions experience heavy rainfall. Others remain unusually warm. Snowfall patterns change. Water reserves, which depend on snowpack, can be affected. And all of these changes are connected, not isolated events, but parts of a larger system, driven by the redistribution of heat across the Pacific. But the impact of extreme events is not limited to land. It extends into the ocean itself. Because when surface waters warm, marine ecosystems are affected. Coral reefs, which depend on stable temperatures, begin to experience stress. If temperatures remain high for too long, coral bleaching occurs. The coral expels the algae that live within it, losing its color, and more importantly, its primary source of energy. If conditions do not improve, the coral dies, and with it, the ecosystems that depend on it. Fish, invertebrates, entire marine communities, all affected by a change in temperature. This is one of the most visible impacts of extreme El Niño events, because it leaves a lasting mark. Not just temporary disruption, but long-term damage. And while ecosystems can recover, the process takes time, sometimes decades. And if extreme events become more frequent, recovery becomes more difficult. This raises an important question. Are these events becoming more common or more intense? And the answer is not simple, because the climate system is influenced by many factors: natural cycles, long-term trends, human activity, all interacting. Some studies suggest that warming global temperatures may increase the likelihood of extreme El Niño events by adding more heat to the ocean, providing more energy to the system. And while this is still being studied, the possibility cannot be ignored, because if extreme events become more frequent, their impact will increase on ecosystems, on weather patterns, and on human societies. But even without that uncertainty, one thing is clear: extreme El Niño events are powerful. they amplify the natural cycle, turning gradual changes into significant disruptions. And they remind us that the balance of the climate system can shift, sometimes slowly, sometimes suddenly, but always with consequences. And yet, even these extreme events are temporary. They do not last forever. Eventually, the feedback loop weakens. The winds begin to recover. The ocean shifts again, and the system moves toward balance or toward its opposite phase, because ENSO is not defined by a single state. It is a cycle, a continuous movement between phases, each one influencing the next, each one shaping the conditions that follow. And understanding these extreme moments is part of understanding the system as a whole, because they reveal its limits, its sensitivity, and its ability to affect the entire planet, from a single region of ocean, through the movement of heat and the response of the atmosphere. A reminder that even the largest systems can be influenced by small changes when those changes are amplified and allowed to grow into something much larger. When we think about El Niño, we often imagine the obvious: floods, droughts, fires, events that appear suddenly and demand attention. But not all of its effects are so visible. Some are quieter, slower, and easier to overlook. Yet they can be just as important, because El Niño does not only change weather, it changes systems, subtle processes that operate in the background of everyday life. And these changes can last long after the event itself has passed. One of the first places this becomes clear is in the ocean. When surface waters warm and upwelling weakens, the supply of nutrients declines. This affects phytoplankton, microscopic organisms that form the foundation of marine ecosystems. They may be invisible, but their role is enormous. They feed fish. They support entire food chains. And they produce a significant portion of the oxygen we breathe. So when their numbers drop, the effects ripple outward. Fish populations decline. Predators struggle to find food. And ecosystems shift. Not always dramatically, but persistently. In some regions, these changes can alter the balance for years, because recovery takes time, and the system does not reset instantly. It adjusts gradually, returning to equilibrium, but often in a slightly different state. And this is only one example, because El Niño also influences something less obvious: the global carbon cycle, the movement of carbon between ocean, atmosphere, and land. Under normal conditions, the ocean absorbs large amounts of carbon dioxide, helping to regulate the planet's climate. But during El Niño, this process can weaken. Warmer waters absorb less carbon, and changes in ocean circulation can release stored carbon back into the atmosphere. At the same time, drought conditions on land can reduce the ability of forests to absorb carbon, and in some cases, increase the likelihood of wildfires, which release carbon as well. These are not immediate effects. They are gradual accumulating over time, but they influence the broader climate system. Connecting El Niño to long-term environmental changes. Another subtle impact can be found in agriculture, not just through obvious droughts or floods, but through timing, because crops depend on predictable seasons, on rainfall arriving at the right moment, on temperatures remaining within certain ranges. Even small shifts can affect yields. Rain that comes too early or too late can disrupt planting cycles. Heat waves can stress crops, reducing productivity, and these changes may not always be immediately visible, but over time, they influence food supply, prices, and availability. In some regions, farmers adapt, adjusting planting schedules, choosing different crops. But adaptation takes time, and not all changes can be easily managed, especially when patterns become less predictable. And unpredictability is one of the defining features of ENSO, because while the cycle repeats, its effects vary, making it difficult to plan with certainty. Another area often overlooked is the impact on health, because changes in temperature and rainfall can influence the spread of disease. Mosquito populations, for example, depend on water and warmth. During El Niño, increased rainfall in some regions can create more breeding sites, allowing populations to grow, and with them, the potential for disease transmission. In other regions, drought can force people to rely on unsafe water sources, increasing the risk of waterborne illness. These effects are not always immediate. They develop over time, often unnoticed until they reach a threshold, and then they become visible. But by that point, the underlying conditions have already been shaped. This is what makes El Niño so complex. It operates on multiple levels. Some effects are rapid, others are slow. Some are obvious, others are hidden. But all are connected because they originate from the same shift, a change in wind and water in one part of the ocean. And this connection extends even further into ecosystems that depend on stability. Coral reefs, as we've seen, are highly sensitive to temperature, but so are many other systems. Forests, wetlands, grasslands. Each responds differently. Each has its own thresholds. And when those thresholds are crossed, change occurs. Sometimes reversible, sometimes not. And over time, these changes accumulate, shaping the environment, influencing biodiversity, altering the balance between species, not through a single event, but through repeated cycles, each one leaving a mark, some small, some significant, but all part of a larger pattern. And this pattern is not isolated to the present. It has been occurring for centuries, long before it was measured, long before it was understood. And it will continue, because ENSO is a natural part of Earth's climate, a system that redistributes heat, maintains balance, and occasionally disrupts it. But as the global climate changes, the context in which this cycle operates is also changing. Ocean temperatures are rising. Atmospheric conditions are shifting. And these changes may influence how ENSO behaves, making some effects more pronounced or more frequent. But this is still an area of research because the system is complex and long-term trends take time to understand. Yet even without that uncertainty, one thing remains clear. El Niño is not just about extreme events. It is about subtle change, processes that unfold quietly, influencing systems that are often overlooked, but essential because they support life, regulate climate, and connect different parts of the planet in ways that are not always visible, but always present. A reminder that the most significant changes are not always the ones we see, but the ones that happen beneath the surface, slowly, continuously, and across the entire Earth. By now, we've seen how El Niño moves through the ocean, how it shifts the atmosphere, how it alters ecosystems, sometimes suddenly, sometimes quietly. But there is another layer to this story, because these changes do not happen in isolation. They reach into human life, into the systems we depend on, into the routines we rarely question. And when El Niño shifts the planet, it also shifts us, not always in obvious ways, but in ways that accumulate over time. Consider something simple. Water. In many parts of the world, water availability depends on seasonal rainfall. Rivers, reservoirs, groundwater, all linked to patterns that are usually predictable. But during El Niño, those patterns can change. Rain may arrive in excess or fail to arrive at all. In regions that depend on steady rainfall, this creates uncertainty. Too much water can overwhelm systems, flood infrastructure, damage homes, disrupt transportation, while too little water creates a different challenge. Drought, reduced water supply, increased demand, and difficult decisions about allocation between agriculture, industry, and daily use. This is one of the most direct ways El Niño affects human life, through resources, but the effects extend further into food systems. Because agriculture depends on stability, on predictable conditions, on the timing of seasons. When those conditions shift, production changes. Crops may fail, yields may decrease, or in some cases, increase unexpectedly. But unpredictability is difficult to manage. Farmers plan months in advance, sometimes years. And when patterns change, those plans must change as well, often with limited time and limited information. This creates risk, not just for individuals, but for entire regions, because agriculture is connected to markets, to supply chains, to economies. A shift in one region can influence prices in another. Availability in one country can affect demand in another. And so, a change in the Pacific Ocean can influence food systems around the world. But El Niño does not only affect what we produce, it affects how we live. In coastal regions, flooding can force relocation. Communities may need to move, temporarily or permanently. Infrastructure may be damaged. Roads, bridges, utilities, systems that support daily life. And rebuilding takes time, resources, planning. In drought-prone areas, the challenge is different. Water conservation becomes essential. Usage must be reduced. Priorities must be set. And sometimes, restrictions are imposed. A reminder that resources are not unlimited, that they depend on systems that can change. There is also an economic dimension, because weather influences productivity, agriculture, energy, transportation, all affected. Drought can reduce hydroelectric power. Flooding can disrupt supply routes. Heat waves can increase energy demand. Each of these factors has economic consequences, not always immediately visible, but measurable over time. And then there is something less tangible, but equally important: perception, the way people understand the environment around them. For many, weather is part of routine, something expected, something familiar. But when patterns change, that sense of familiarity can shift. Events that were once rare become more common or more intense. And this can influence how people think about the future, about risk, about stability. Because El Niño highlights something fundamental: that the systems we depend on are dynamic, not fixed, not guaranteed. And this awareness can lead to adaptation, changes in behavior, in planning, in how communities prepare for uncertainty. Some regions have already begun to adapt, improving forecasting systems, building infrastructure designed to withstand extremes, developing strategies for water management, and agriculture that can respond to changing conditions. These adaptations are not immediate. They develop over time, through experience, through observation, through learning. And ENSO plays a role in that learning, because it provides repeated events, opportunities to observe patterns, to test responses, to refine strategies. But adaptation is not uniform. Not all regions have the same resources. Not all communities have the same capacity to respond, which means the impact of El Niño can vary, not just in terms of weather, but in terms of resilience. Some areas recover quickly, others take longer, and some face challenges that extend beyond a single event. But even within these differences, there is a shared connection. Because El Niño affects multiple regions at once, linking distant communities through a common system, a reminder that the planet operates as a whole, that changes in one place can influence conditions in another. And that understanding these connections is essential, not just for science, but for society. Because the more we understand, the better we can prepare, not for a specific event, but for a range of possibilities, for variability, for uncertainty, for change. And in this sense, El Niño is not just a climate phenomenon. It is a lesson, a demonstration of how interconnected systems behave, how they influence life, and how that influence can be managed, not controlled, but understood, and through understanding, adapted to, because the cycle will continue, shifting between phases, altering conditions, and shaping the environment. And with each cycle, we gain more insight, more data, more experience, building a clearer picture of how the system works and how we can live within it. A quiet process, but an important one, because it connects science to everyday life in ways that are not always visible, but always present across the entire planet. After everything we've explored, one idea remains. We understand El Niño, and yet we don't fully understand it. We know how it begins. We know how it moves through the ocean. We know how it alters the atmosphere. And we know the effects it can produce. Floods, droughts, shifts in temperature, changes in ecosystems. We can observe it, measure it, track it in real time, and even predict it to a certain extent. But prediction is not the same as certainty, because the system itself is complex. Not just complicated, but interconnected. Multiple processes operating at the same time, influencing each other, sometimes reinforcing, sometimes cancelling out. And this creates uncertainty, even with the most advanced tools, even with decades of data. There are still moments when the system behaves in unexpected ways. Events that develop differently than predicted, stronger than expected, or weaker, arriving earlier or later, and sometimes not forming at all. This is one of the challenges of studying ENSO. It is not a simple cycle. It does not repeat with precision. It varies, responding to subtle changes in the environment. And those changes are not always easy to detect, because some of them begin far below the surface, in layers of the ocean that are not directly visible, where temperature gradients shift, where currents move slowly, carrying heat across vast distances. These processes take time, weeks, months, sometimes longer, and by the time their effects reach the surface, they have already shaped the conditions, making it difficult to trace cause and effect. Another source of uncertainty comes from the atmosphere, because the atmosphere is dynamic, constantly changing, influenced by factors beyond the Pacific Ocean. Seasonal cycles, solar energy, land surface conditions, all interacting, all contributing to the overall behavior of the system. Which means that ENSO does not operate in isolation. It is part of a larger network, and understanding that network is an ongoing process. Because every time we learn something new, new questions appear. Why do some El Niño events become extreme? Why do others remain mild? What determines their duration? What triggers their end? These questions do not always have clear answers. Not yet, but they are part of the process of understanding. Because science is not about having all the answers. It is about refining them, improving models, testing predictions, and adjusting based on new information. And over time, this process leads to progress. Gradual, incremental, but meaningful. Because even partial understanding can make a difference. It allows better forecasting, better preparation, better responses to changing conditions. But there is another layer to this uncertainty, one that extends beyond the cycle itself, the influence of long-term climate change. Because the Earth is warming, ocean temperatures are rising, atmospheric conditions are shifting, and these changes may influence how ENSO behaves. But the exact relationship is not fully understood. Some research suggests that warmer oceans may increase the intensity of El Niño events, providing more energy to the system, allowing stronger feedback loops. Other studies suggest that variability may increase, making the cycle less predictable, or that the frequency of extreme events may change. But these are still areas of active research, because the climate system is complex, and long-term trends take time to reveal themselves, which means that ENSO exists at the intersection of natural variability and ongoing change. A system that has always been present, now operating within a shifting environment. And this makes understanding it even more important. Because the better we understand the system, the better we can anticipate its behavior, even if we cannot predict it perfectly. Even if uncertainty remains. But uncertainty is not a limitation. It is a characteristic, a reflection of the complexity of the system. And in many ways, it is what drives further exploration, because unanswered questions lead to new research, new data, new insights, and over time, a clearer picture emerges, not complete, but increasingly detailed. And this process does not end, because the system continues to evolve, responding to changes, adapting to new conditions, and providing new information. With each cycle, each El Niño, each La Niña, adding to the record, expanding our understanding, but never fully resolving it, because the Earth's climate is not static. It is dynamic, and understanding a dynamic system is an ongoing process, one that requires observation, patience, and the ability to adapt. Just as the system itself adapts, and this leads to a broader realization that even with advanced technology, with detailed models, with global observation networks, there are still limits. Not absolute limits, but practical ones. Limits in data, limits in resolution, limits in the ability to capture every variable. And these limits remind us that understanding is always evolving, always improving, but never complete. And perhaps that is what makes systems like ENSO so fascinating, because they exist at the edge of understanding, where knowledge meets uncertainty, where patterns can be seen but not always predicted, and where each new discovery leads to deeper questions about the ocean, the atmosphere, and the connections between them. A reminder that even on a planet we inhabit, there are processes that remain partially unknown, not hidden, but complex, waiting to be explored further. With each passing cycle, after everything we've explored, from shifting winds to moving oceans, from hidden currents to global weather, one idea remains. El Niño is not an anomaly. It is not a mistake in the system. It is part of how the planet works. A natural cycle moving between phases, adjusting, redistributing energy, maintaining a form of balance that is never fixed. Because balance on Earth is not still. It is dynamic, always shifting, always responding. And ENSO is one of the clearest examples of that. A system where ocean and atmosphere interact continuously, where heat is transferred from one region to another, where changes in one place are reflected in another. This interaction has been happening for as long as the oceans have existed, long before it was named, long before it was measured, long before it was understood. And it will continue, because the forces that drive it are fundamental. The rotation of the Earth, the uneven heating of the planet, the movement of air, the flow of water, all working together, all shaping the system. But while ENSO is natural, its context is changing. The planet is warming. Ocean temperatures are rising. Atmospheric conditions are shifting. And these changes may influence the cycle, not by replacing it, but by altering its behavior, making some events more intense, or changing their frequency, or increasing variability. But these effects are not yet fully understood. They are still being studied, still being observed, because long-term changes take time to reveal themselves. And the climate system is complex. It does not respond in simple ways. But even without complete certainty, there is something important to recognize: that ENSO is not separate from the larger climate system. It is part of it, and understanding it helps us understand the planet, not just in terms of weather, but in terms of connection. Because everything we've explored points to one idea: interconnection. The ocean influencing the atmosphere influencing land influencing ecosystems, and ecosystems influencing life. All linked, all part of a single system. And this system does not operate in isolation. Human activity has become part of it, through energy use, through land use, through the release of greenhouse gases. And these influences interact with natural cycles, sometimes amplifying them, sometimes modifying them, adding another layer of complexity, which makes understanding even more important. Not just for knowledge, but for adaptation. Because while we cannot control ENSO, we can respond to it. We can prepare for its effects, plan for variability, design systems that are resilient, that can withstand change, that can adapt. And this is already happening in agriculture, in water management, in disaster planning, using forecasts, using data, using an understanding of patterns to reduce risk and improve outcomes. But adaptation is not only about infrastructure. It is also about awareness. Understanding that the environment is dynamic, that patterns can change, that stability is not guaranteed, and that flexibility is essential. Because ENSO reminds us that even large systems can shift, sometimes gradually, sometimes quickly, but always with consequences. And these consequences are not always negative. In some regions, El Niño can bring beneficial rainfall, supporting agriculture, replenishing water supplies. In others, La Niña can enhance marine productivity, supporting fisheries, providing resources. So the cycle is not inherently harmful. It is variable, producing both challenges and opportunities, depending on location, timing, and intensity. And this variability is part of the system, part of what allows the Earth to redistribute energy, to adjust to changing conditions, to maintain a dynamic equilibrium. But for those living within this system, the experience can be different, because variability introduces uncertainty. And uncertainty requires adaptation, requires planning, requires understanding. And this is where knowledge becomes valuable, not just in explaining what happens, but in helping us respond. Because the more we understand, the more effectively we can adapt, not to eliminate change, but to live with it, to anticipate it, to prepare for it, and to reduce its impact. This is the role of science: to observe, to understand, to inform, and through that, to support resilience. But beyond all of this, there is a broader perspective. Because ENSO is not just a climate cycle. It is a window into how the planet functions, how different systems interact, how energy moves, how balance is maintained, and how change occurs, not as isolated events, but as part of a continuous process, a process that has been unfolding for millions of years and will continue long into the future. And in that sense, El Niño is not just something that happens to the planet. It is something that defines it, a reflection of its complexity, its dynamism, its interconnected nature. And understanding it is part of understanding the world we live in, not as a static environment, but as a system in motion, always changing, always adapting, and always connected, from the deepest ocean currents to the highest layers of the atmosphere. A quiet balance that is never still, but always evolving. Across the entire Earth, after everything we've explored, from shifting winds to warming oceans, from quiet changes beneath the surface to global consequences, one question remains: what happens next? not just in the next cycle, but in the years and decades ahead. Because El Niño is not a single event. It is part of a system, a cycle that has repeated for centuries. But now, that cycle exists within a changing world. A world where temperatures are rising, where oceans are storing more heat, where the atmosphere is holding more moisture. And these changes matter because they influence the background conditions on which ENSO operates. They do not replace the cycle, but they can shape it, alter its intensity, its timing, its impact. And this is where uncertainty becomes important. Because while we understand the mechanics of El Niño, we do not yet fully understand how it will behave in a warmer climate. Some models suggest that extreme events may become more frequent because additional heat in the ocean provides more energy to the system, allowing stronger feedback loops, stronger disruptions. Other research suggests that variability may increase, making the cycle less predictable, less consistent, and potentially more difficult to forecast. But these are possibilities, not certainties, because the climate system is complex, and long-term trends take time to emerge clearly, which means that observation continues. Data continues to be collected. Models continue to improve. And with each new cycle, we learn more, refining our understanding, adjusting our expectations. But while the science develops, something else is already happening. Adaptation. Across the world, communities are responding to variability, not just to individual events, but to the patterns behind them. In agriculture, farmers are adjusting planting strategies, choosing crops that can tolerate a wider range of conditions, using forecasting tools to anticipate rainfall changes, and planning accordingly. In water management, systems are being redesigned, reservoirs expanded, conservation measures implemented to handle both excess and shortage. In coastal regions, infrastructure is being reinforced, flood defenses improved, urban planning adjusted to account for changing risks. These changes are not immediate. They develop over time, through experience, through observation, through learning. And ENSO plays a role in that process because it provides repeated events, opportunities to observe, to test responses, to improve resilience. But adaptation is not uniform. Not all regions have the same resources. Not all communities can respond equally, which means that vulnerability remains. In some areas, the impact of El Niño is still severe, still difficult to manage. And this highlights another aspect of the system: its uneven effects. Because while ENSO is global, its impacts are not distributed equally. Some regions experience significant changes, others only minor variations. And this creates differences in how the cycle is experienced. But regardless of location, the underlying system is the same: a continuous movement of energy across ocean and atmosphere, shaping conditions, influencing outcomes. And as long as that system exists, so will the cycle. El Niño, La Niña, neutral phases, repeating, shifting, adapting. But the future of this cycle is not only about natural processes. It is also about how we understand them, how we respond, and how we integrate that understanding into the systems we build. Because knowledge changes outcomes. It allows preparation, reduces risk, and supports resilience, not by eliminating variability, but by working with it. And this approach extends beyond Earth, because understanding climate systems is not only important for our planet, it is essential for exploring others. If humans ever attempt to live beyond Earth, to settle on other planets, or even reshape them, we will need to understand how climate systems behave, how atmosphere and surface interact, how feedback loops develop, and how stability can be maintained. ENSO provides a model, a natural example of how complex systems operate, how they respond to changes, and how they influence their environment. A system we can observe, measure, and learn from. But even with that knowledge, there is still uncertainty, because no system is identical. No planet is exactly the same. And variability is always present, which means that understanding is always evolving, always improving, but never complete. And perhaps that is what makes systems like ENSO so important. Not just for what they reveal, but for what they teach. About complexity, about connection, about the relationship between stability and change. Because the Earth is not static. It is dynamic, always adjusting, always responding. And ENSO is one of the ways it does that. A cycle that redistributes heat, balances energy, and occasionally disrupts the patterns we expect. But in doing so, it reminds us of something fundamental, that the environment we live in is not fixed. It is part of a larger system, one that is always in motion, always evolving, and always connected from the deepest ocean currents to the highest layers of the atmosphere. And as we move forward, that understanding becomes more important. Not just for predicting the next event, but for living within a system that is constantly changing and learning to adapt, to respond, and to understand the quiet balance of a changing planet. In the end, El Niño is not just about weather. It is not only about rain or drought or shifting winds across the Pacific. It is something deeper, a pattern, a quiet rhythm that exists within the larger system of the Earth. A reminder that the planet is not still, not fixed, but always moving, always adjusting. From the surface of the ocean to the highest layers of the atmosphere, everything is connected. Everything is part of a continuous exchange. Heat moving across water, air rising and falling, pressure shifting, currents flowing. And within this movement, balance is maintained. Not perfectly, not permanently, but dynamically, Because balance on Earth is not about stillness. It is about change, a constant process of correction, of adjustment, of redistribution. And ENSO is one expression of that process. A cycle that redistributes heat across the planet, shifting energy from one region to another, altering patterns, influencing systems, and in doing so, maintaining a larger equilibrium, even when it appears disruptive, even when its effects feel extreme. Because disruption is part of balance. Without variation, there is no adjustment. Without adjustment, there is no stability. And this idea extends beyond El Niño. It applies to the entire climate system, to the oceans, the atmosphere, the land, and the life that depends on them, all interacting, all responding, all shaping the environment in which we live. And within this system, humans are not separate. We are part of it, influenced by it, dependent on it, and increasingly affecting it through our actions, through the systems we build, through the ways we use energy and resources. And this interaction adds another layer, another set of influences that combine with natural cycles, creating new patterns, new outcomes, and new challenges, but also new opportunities for understanding. Because as we study these systems, as we observe how they behave, we gain insight, not just into the environment, but into how complex systems function, how they respond to change, how they maintain balance, and how they can be influenced. This knowledge is not abstract. It has practical meaning. It informs decisions, guides planning, supports adaptation, and helps us live within a system that is always evolving. Because the goal is not to stop change. That is not possible. The goal is to understand it, to anticipate it, to respond in ways that reduce harm and support resilience. And ENSO provides a framework for that understanding. A repeating cycle, a natural experiment, playing out across the Pacific Ocean, showing us how the planet behaves and how it responds to variation. But beyond the science, there is also perspective. Because when we look at El Niño, we are looking at a system that operates on a global scale, connecting distant regions, linking ocean and atmosphere, influencing ecosystems and human societies, all through the movement of heat and air. And this scale can change how we see the world, not as separate parts, but as a connected whole, where actions in one place can influence outcomes in another, where systems overlap, interact, and evolve together. This perspective is important because it encourages a broader understanding, one that goes beyond local conditions and considers global interactions, which are increasingly relevant in a world where changes are interconnected. And this brings us back to the beginning, to the Pacific Ocean, to the winds, to the movement of water. A simple shift that sets everything in motion. A reminder that even the largest systems can be influenced by subtle changes, and that those changes can travel, expand, and shape the world in ways we may not immediately see, but can learn to understand over time, through observation, through study, through patience. And as we continue to learn, the picture becomes clearer, not complete, but more detailed, more connected, more reflective of the system as a whole. And in that clarity, there is something else, a sense of scale, an awareness of the complexity of the world we live in, and the processes that sustain it, processes that operate quietly, continuously, often unnoticed, but always present. From the deepest ocean currents to the highest winds in the atmosphere, a quiet pattern behind everything, always moving, always changing, and always shaping the Earth. At this point, the movement of the planet begins to feel familiar. The ocean shifts, the winds respond, the atmosphere adjusts, and slowly, the system finds its way forward, not toward a fixed state, but toward another moment of balance, temporary, changing, always part of a larger rhythm. And as this rhythm continues, it becomes less like an event and more like a presence, something that is always there, even when we are not aware of it, because most of the time, these changes happen quietly, far from where we live, far beneath the surface, in places we do not see, but still, they influence the world around us. The weather outside, the temperature of the air, the availability of water, the patterns that shape daily life, all connected, all part of a system that is always in motion. And yet, for long periods, that motion feels stable, predictable, reliable, until it isn't, until something shifts, until the familiar pattern changes and reminds us that stability is not permanent, that it is something the system creates again and again, through adjustment, through variation, through cycles like El Niño and La Niña. And once we begin to see this pattern, it becomes difficult to unsee, because it appears everywhere, in the ocean currents, in the movement of clouds, in the rise and fall of temperature, even in the smallest changes, subtle signals that something is adjusting, something is responding, and this response is constant, not tied to a single event, but part of an ongoing process, a process that does not begin or end in any single moment, because the Earth does not pause, it does not reset, it moves forward continuously, each cycle influencing the next, each shift leaving a trace, a small adjustment in the larger system. And over time, these adjustments accumulate, shaping the environment, altering conditions, creating the patterns we recognize as climate. But within those patterns, there is variation, always, because no system remains exactly the same, even when it appears stable. There are always forces at work, gradual changes, slow movements, that eventually become visible. And ENSO is one of the ways those changes reveal themselves. a cycle that brings hidden processes to the surface, making them visible, observable, understandable, at least in part. But even as we understand more, the system remains open, still evolving, still responding, and still capable of surprising us. Because complexity allows for variation, for outcomes that are not identical, even when the underlying pattern is the same. And this variation is not a flaw. It is a feature, a reflection of the system's ability to adapt, to adjust to changing conditions, to maintain balance through movement, through change, through cycles. And as we observe this, something else becomes clear: that our place within this system is not separate. We are part of it, affected by it, responding to it, and increasingly influencing it through the choices we make, through the systems we build, through the ways we interact with the environment. And this connection carries responsibility, not to control the system, but to understand it, to recognize its patterns, to anticipate its changes, and to respond in ways that support balance, not just for ourselves, but for the systems that sustain life. Because the ocean, the atmosphere, the land, and the life within them are not isolated. They are interconnected, dependent on each other, and influenced by cycles like ENSO, which continue whether we observe them or not, shifting between phases, adjusting conditions, and shaping the world, quietly, continuously. And as this understanding settles in, there is a different perspective, a slower one, less focused on individual events and more on the pattern itself, on the rhythm of change, on the movement of the system. And in that perspective, there is a sense of continuity, a recognition that the planet is always active, always evolving, and always connected. From the smallest particle of plankton to the largest currents of air, from the deepest layers of the ocean to the highest reaches of the atmosphere, all part of the same process. A process that does not stop, does not reset, but flows from one state to another, from one balance to the next. And as it flows, it shapes everything: the environment, the conditions of life, and the experiences of those who live within it, including us. And so, as we step back from the details, from the measurements, from the definitions, what remains is the pattern, a quiet pattern, subtle, continuous, and always present, a reminder that the world is not still, but in motion, and that motion is what sustains it, what defines it, and what connects everything within it. As the cycle continues and the system moves forward, the pattern remains quiet, steady, and always unfolding beneath the surface of everything we see, even after a cycle fades, even after the winds return to normal, even after the ocean appears calm again. Nothing truly resets, because the ocean remembers. Not in the way we remember, with thoughts or images, but through energy, through heat stored in its depths, through currents that continue to move, long after the surface has changed. And this memory matters because it influences what happens next. Every El Niño, every La Niña leaves behind a trace, a redistribution of heat, a shift in temperature patterns, a subtle change in the structure of the ocean. These changes do not disappear instantly. They linger, slowly dispersing, slowly blending back into the system, but never completely erased, because the ocean is vast and movement within it is slow, much slower than the atmosphere. While winds can change in hours or days, ocean currents can take months or even years, carrying heat across long distances, from one region to another, from one phase of the cycle into the next. This is why ENSO is not a series of isolated events. It is continuous, each phase influenced by what came before, each shift shaped by lingering conditions. A chain rather than a sequence. And at the center of this chain is heat, because heat drives the system. It determines how water moves, how air responds, how pressure changes, and how the cycle evolves. When warm water spreads during El Niño, it does not vanish when the event ends. It is redistributed. Some of it sinks. Some of it moves west again. Some of it spreads into other ocean regions, becoming part of the background state. And this background state influences the next phase, sometimes supporting a transition into La Niña, sometimes delaying it, sometimes creating neutral conditions. This is why timing varies, why the cycle does not follow a strict pattern, because each new phase begins not from zero, but from what remains, from the memory of the ocean. And this memory is not only about temperature. It also involves structure, the layering of water, the difference between warm surface layers and colder depths. These layers shift over time, becoming thicker or thinner depending on conditions. And these changes affect how easily heat can move, how quickly it can rise or sink, and how strongly the system responds. This adds another layer of complexity, because the system is not only reacting to present conditions, but also to its own history, a history stored in the ocean itself. And this history extends beyond ENSO, because the ocean interacts with other systems, longer-term cycles, global temperature trends, deep ocean currents that circulate around the planet, all contributing to the overall state, all influencing how ENSO behaves. And this is where the scale becomes clear. Because while ENSO may appear as a regional phenomenon, it is connected to global processes that operate over much longer timescales, decades, centuries, even longer. And within these timescales, the ocean continues to store and move heat, acting as a regulator, absorbing energy, releasing it, maintaining a form of balance, but not a static one, a dynamic equilibrium, constantly adjusting. And ENSO is one of the ways this adjustment becomes visible, a surface expression of deeper processes that are usually hidden. but always active. And this brings us to another idea, that what we observe is only part of the system. The visible changes, the shifts in weather, the variations in temperature, these are the surface. Beneath them, there is a deeper layer, a slower movement, a longer memory. And understanding that layer is essential because it helps explain why the system behaves the way it does, why patterns repeat, but not exactly, why events vary in intensity, in duration, in timing, and why prediction remains uncertain. Because to predict the future, we must understand the present and the past, both of which are stored within the ocean. And this understanding continues to grow with new observations, with improved models, with better tools, allowing scientists to see deeper, to measure more precisely, to track changes over time. But even with these advances, the system remains complex because the ocean is vast and its processes are intricate, interconnected, influenced by multiple factors, which means that understanding is always evolving, always improving, but never complete. And perhaps that is part of what makes it so fascinating, because it reveals a system that is both stable and variable, predictable in pattern, but unpredictable in detail. A balance between order and change. And within that balance, the memory of the ocean continues, carrying heat, shaping currents, influencing the atmosphere, and setting the stage for the next shift, the next phase, the next movement in the cycle. A reminder that nothing truly begins from nothing, and nothing truly ends, but instead, everything flows from one state into another, guided by forces that operate quietly, continuously, and across the entire planet, from the deepest waters to the surface we see. A long memory held within the ocean itself, always present, always shaping what comes next.